Hi everyone, this is Adam Green here from ATA Engineering. Thank you for joining us for this afternoon's webinar on SPH Multiphase model in STAR-CCM Plus. I'm joined by ATA's Chris Stoich and Mark Russell. Chris is an expert in STAR-CCM Plus and CFD General, and Mark is certainly an expert in CFD and STAR and SPH Flow. So welcome those two, and we'll dive into the webinar. Just a few notes. Everybody's mic is muted until the end of the webinar, when we'll open them up for questions. If you have questions in the meantime, please put them in the chat. Thank you. So a little bit about ATA Engineering. We are an employee-owned small business. We have over 200 people on staff, all of whom are owners of the company, and over 40 of those, says 38 there, but over 40 of those are PhDs, and over 95 are masters in engineering. And so you can see we have a very skilled group of folk doing very high-end consulting engineering. And the industries that we do that in range from aerospace and defense through spacecraft and the maritime industries. And then we also do a lot of work on themed entertainment. And so it's kind of a diverse set of industries, but it's certainly areas that we all enjoy working on. And so the kind of things that we do is really design, analysis, and test, right the way through from initial concept and structural design, analysis with many simulation tools, including Siemens. And then also the mainstay of our business is test, structural testing service for extreme loading. So a lot of that is in the aerospace side, doing ground vehicle testing for large aero structures to look at their performance. And where do we do that? We have teams that actually travel all over from the US, but we have offices mostly in the centers of aerospace within the US, from the West Coast through Denver and Albuquerque and Huntsville in Alabama, and then on the East Coast we have Washington D.C. and very recently Boston as well. So and really, to do the work we do, we use a lot of analysis tools, and we use a lot of Siemens analysis tools because we believe they're the best. And because of that, we also sell them and support them. And we are a Siemens Platinum level solutions partner. Platinum is the top level, and basically our skills in this space, in their software, together with the volume that we do, makes us a Platinum level partner. And so what do we do for Siemens? Well, we do a lot of things. We do support for our clients who buy Siemens software through us. So we have software support and hotline support, and also software implementation for people who need help to kind of install and roll it out. And really, when we look at the tools that Siemens provides, we focus mostly on the Simcenter side, Simcenter and analysis. So NX, Nastran, VMAP, STAR-CCM Plus especially, and then AIM-Sim, Simcenter 1D, Simcenter 3D, and also Teamcenter. So the whole suite of really digital thread tools from Siemens we work on. We also do a lot of training for Nastran and VMAP, and we're also a preferred trainer for Siemens for those products, and including STAR-CCM Plus. And so we are very connected with Siemens, and really, the history of ATA indicates why we're so connected to Siemens, and that is that SDRC was a company in Ohio that originally ATA was a group within SDRC, and SDRC created ideas and graphics, which ultimately became NX. And so ATA has had over a 30-year connection with NX, and you can see that over the years. In 2007 we became a partner, and we've slowly grown that to being a partner supporting STAR and HEEDS, and most recently test and measurement. We've started supporting the Siemens tools for that. And so we really now cover all the things that within the Siemens portfolio that really gel with our expertise. So we're pretty excited to work, especially with the new test and measurement equipment. And so on the software side, we really focus on Simcenter, Teamcenter, and NX CAD and CAM as well. So within our particularly in our STAR-CCM Plus group, we have 7 team members who do consulting engineering all the time, and as part of that work, they also support our customers. And it's a very nice model where our engineers get to use the tools in anger daily, but also help our clients using the tools, really try the difficult problems. And we have similar teams for FEMAP, NASTRAN, and HEEDS and AIMSIM as well. So we really connect well with the tools. We use them very powerfully, and we use that experience to provide great support to our clients. And all of this can be found on our website, so please visit that, ata.com/software. You can really find all of these things, including the project inquiries and also our hotline support access. So today we are going to talk about, obviously, a couple of things. One is STAR-CCM Plus and its multi-phase features. But really the goal of that is to introduce us to the new SPH multi-phase model in STAR-CCM Plus. And then the team, Mark and Chris, are going to demonstrate SPH Flow actually working, and so you can see how easy it is to deliver some of these advanced multi-phase results. So let's look at STAR-CCM Plus for a little bit. We're not really going to focus on this today in terms of total details, but really the vision of the product is, and it delivers very well, is that it's a complete integrated multiphysics CFD tool, and it's an integrated environment. It's very automated. That the multiphysics are really amazing in terms of it'll do almost all physics you can think of. It has a lot of automation for built-in design exploration. It also can run in parallel, including meshing on massive computers. So if you want to mesh and run on thousands, I think they've done over 1 million cores in very big models and STAR still scales well on that, right the way through from PLM integration to Teamcenter and others, and also very customer focused. So it's a really comprehensive CFD tool. And so we're not here to talk about that totally today, but it is an intro for what we'll need to consider later. And so when we talk about that, one of the comprehensive multiphysics pieces of STAR is really just the broad range of physical models, and especially the broad range of multi-phase flows that we're going to talk about in a minute. But you can see on the right there, I won't read them all out, but there are a lot of various physical models in STAR that really help engineers and designers tackle real-world problems. And so right the way through from just using the right physics, including motion, including different analysis tools that can be coupled together to cover all the bases, and ultimately fluid structure interaction to do a CFD model coupled to a structural model to give very meaningful answers to complex problems. And so you can see that the list of multi-phase applications, especially in STAR, is quite diverse from evaporating condensers, standard flows through spray painting to Lagrangian flows, additive manufacturing, and then at the bottom there you can see powertrain lubrication. That's the SPH Flow. Coding is DEM, and then volume of fluid method is spillways on the right there. But just the list of multi-phase models alone in STAR is very comprehensive. And so here's the list of multi-phase models that there are, and there's 8 altogether. And when you look at those, there's kind of 2 groups. Really, there is Eulerian and Lagrangian style multi-phase models, and so that's how they break it up. And we can see that, and when we look at it this way, where we've got the groups of tools together, and if we move those, we can see that on the left of the line we've got the Eulerian models, kind of continuous phases moving through each other, and then Lagrangian models on the right, which are more particle-based and sometimes coupled. DEM is fully coupled to both a CFD model and the particle model. SPH Flow is newer to STAR and is less coupled, but really both extending the range of physical multi-phase modeling that can be done with each type of model or analysis. So when we go through the list in terms of the Eulerian multiphase within STAR, it's really it's kind of the complete multiphase model. It has transport equations in both phases. So it really gives you the ability to do most things, but it's also computationally pretty intensive. So if you want to do bubble flows or fluidized beds, this is the one to use. But you've got to have decent computer systems, and sometimes it can take longer to compute. So there's a few models that are simplified in that regard. The MMP can still let you do a lot of multi-phase, do boiling, that kind of thing, but on a slightly simplified mathematical basis to make it go faster. So it can do boiling, for instance, or nuclear steam generators, but it can process them a lot quicker than excuse me, the full EMP model. And then we get to the volume of fluid model, where you have really kind of water and free surfaces, not necessarily water, but any fluid and free surfaces, and the free surfaces track, and gravity and waves are all part of that simulation. So if you want to do a ship moving through the ocean and you want to look at Kelvin waves around the ship, then this is the model you might use. But obviously that fuel tank sloshing, all kinds of other flows use that same phenomena. And so the volume of fluid model is certainly the one most used in marine applications, but it's also used in a lot of other areas too. And then an extension to that is the fluid film model, where particles can, coagulate onto a surface and then create a thin film that runs down things. So this is kind of a very specialized model to do kind of rainwater management and fuel sprays and coatings, things like that. And also aircraft ice protection is another model that can do that. That also couples with modified mesh generation for ice growing on aircraft wings. And then Lagrangian multiphase, now we're getting into particles, and this one, it's actually not a video, but lets you do fuel sprays, fuel injection, fuel spray into cylinders, liquid fuel combustion, those kind of things. Pretty advanced, and but it's now based on the particles instead of kind of continuous phases. And then the model today we're going to talk about is dispersed multiphase first. Is really another particle model, really to look at vehicle water management and aircraft icing. And again, it's a single phase model, so it's a little bit more efficient, but it's still another variation on the DMP side. And then SPH Flow, which we're going to look at today. This one is actually a video. And really, if you want to look at complex fluid problems, liquid problems, with free surfaces, things like that, then SPH Flow, and it's pretty new in STAR-CCM Plus in the last year, is the one to do that. So doing oil sloshing in a transmission like this example, is pretty intense calculation, but SPH Flow lets you do it. And then lastly, there is DEM. DEM is discrete element modeling, which really lets you model particles. You can define the particles with a CAD tool to define their shape. And then you can actually model the flow and the interaction between the particles, the inertia, the general motion of the particles coupled to the fluid flow. So in DEM in STAR is pretty established, very robust, and can do a lot of things, from looking at blades of grass moving through a mower, to fluidized beds, to rock mechanics and conveying aggregates. So it's very comprehensive, and you can see this kind of example of an excavator digging up particles and moving them around is something that DEM can do. So you can see that STAR-CCM Plus covers a lot of multi-phase problems, and today we're really going to focus on SPH Flow. And so this is really the kind of modeling that SPH Flow can really get great answers from. Very detailed free surface modeling, and especially of water penetration in vehicles passing through water, especially electric vehicles, which is obviously a big deal nowadays. So with that, I thank you, and I will pass the ball to Chris and Mark. Thanks a lot.
A smooth interpolation between the particles is what is used to discretize the governing PDEs. So this is not like similar to the discrete element method, in which you kind of choose like hooking in contact with the particles. You are using basis functions, and you are discretizing the true natural PDEs for these problems. And so the problems where SPH really shine are kind of highlighted by this classic dam break problem that's shown for a lot of SPH work. It's naturally suited for fluid flows that have complex and deforming free surfaces, those with large deformations, potential material splitting, or dynamic material phase interfaces. And Chris, you want to go ahead and play that video there? You can kind of see all of these at work here. So this free surface is very complex. It's moving. Particles are being spread around the domain. And with SPH, you only solve equations where those particles are. So all those voids, all that empty space, that is not a computational burden that you have to carry on. It kind of, because it's mesh free, it only exists where this fluid is, and so it is extremely computationally efficient for these types of problems. So we go on to the next slide, please. So kind of this slide kind of summarizes the key differences between your traditional mesh-based methods and mesh-free particle methods. So, with the mesh-based methods, you have a predefined conductivity of nodal interactions. And kind of the two major flavors of that are, of course, Eulerian mesh, in which your mesh is fixed and your material needs to flow or move through that mesh. And so any kind of movement requires complex schemes for tracking material interfaces and free surfaces. The alternative is a Lagrangian mesh, in which your mesh is bound to the motion of your particles. But the issue is as those particles move or fluid moves, those elements might collapse upon each other, and then you have to have complex schemes for remeshing. So kind of any large deformation or splitting problems become very expensive to solve with those traditional mesh-based approaches. Mesh-free particle methods, on the other hand, they mesh the material geometry as a set of individual quote-unquote particles that have explicit masses and no predefined conductivity. So, each node has a mass and a radius associated with it, and where that node moves is where that actual mass moves in space. And so because of that, they provide a natural and efficient means of modeling a handful of problems. For example, particulate geometries, like Adam showed, is really nicely handled through discrete element method. If you have like a large material movement, for example, like finite plasticity, there's methods like the RKPM code, which is really good method, which is really good for those. And then for fluids with free surfaces, you really can't beat SPH for performance. So next slide, please. But the cool thing about SPH is you aren't making any you're not making any concessions in terms of the math that you're solving by going to a particle method. You are solving the true governing physical PDEs that we're familiar with and we used over the years. Balance of linear momentum, and the continuity equation for CFD type problems. So you solve the true Navier-Stokes equations as you shown here. The discretization is a particle and particle base, and these equations get a little messier when you put them out in true SPH form. But you are solving the true continuity and momentum equations. The one kind of caveat is, while you are solving Navier-Stokes, it is really meant for incompressible or weakly compressible fluids, and kind of extension to rarefied flows or microfluidics is not always directly recommended for this type of model. So this is the only kind of discretization slide I have here. We have a lot more theory we can discuss, but fundamentally, this is what an SPH discretization does. So the governing PDEs are locally integrated at the center of each particle using the field values at neighboring particles convoluted with a weighting function. So that weighting function is shown here on the image on the right. It's a bell-shaped curve. There's many different options for them. A cubic spline is a common one. The kind of two key features of it are that it has a compact radius of support. So it's not infinite radius. You're only talking with maybe 1 to 2 particles away from the node you're solving at, and that the integral of that weighting function over its domain is equal to 1. So that gives you consistency in your solves. The way the particle formulation works is that if you look back on the left, is that you can transform function evaluations or evaluations of the derivative of functions to purely a summation over particle values and the weighting function at those neighboring particle locations. So for example, if we look at f of x, we'll basically sum over the neighboring particles. So neighboring particles are one within the smoothing distance h. We evaluate the function at those neighboring particle values. There's some basically the mass divided by the density of those neighboring particles is to account for the volume that those particles have, because some particles might be larger or smaller than others. And then you evaluate the smoothing function, at that value as well. And that's all it is. So that's why SPH is so fast. It's just you just run through these particle summations, and that's how you can perform your integration. And yeah, so that's kind of the key to the method. And then finally, that grad fx, that shows that you can apply that gradient directly to the basically the smoothing function, so you don't need to worry about taking derivatives of your field variables. So I think that's all the content I had. So again, there's a lot more you can dig into SPH, and maybe we can do that for a future webinar, but that should be enough to kind of give you an overview of where it works. And now I'll pass it off to Chris, who again is our expert in the STAR-CCM plus applications, and he'll run through kind of a specific use case of the SPH implementation.
Hey, thanks a lot, Mark. Yeah, so my name is Chris Stoyich. I'm just going to talk about the SPH implementation in STAR-CCM plus. So I'll start the story, but just saying Simcenter SPH Flow, which is a separate software presented by Siemens, is currently being integrated into STAR-CCM plus as a multiphase model. One benefit of that is STAR-CCM plus has a very efficient architecture, and the current SPH implementation in STAR-CCM plus has been shown to run up to 30% faster than the standalone SPH Flow. So things are looking good so far. STAR-CCM plus 2402 is the first release that includes the SPH multiphase model. Though I should note that an additional license is needed to run this multiphase model. You can set the model up and everything, but once you push go, it checks for that license. The current implementation is incomplete. They're just in the first stages of implementing it, so it's not the entire SPH Flow package in STAR-CCM plus yet, but enough of the features have been implemented to kind of target powertrain lubrication problems. So some of the models needed to do that are gravity, fluid viscosity, particle initialization model. The only boundary conditions currently are just solid wall boundary conditions, and then they allow you to specify rotation of solid bodies. And then you can set up several types of reports and monitors, such as the torque report shown on the lower right, which corresponds to that animation that Adam showed earlier of the 3 gears kind of meshing and running together. So as I mentioned, SPH Flow is being integrated into STAR. So after everything's all said and done, the STAR-CCM plus SPH multiphase model should be very comparable to what's offered through SPH Flow. So this is likely to include 6-DOF dynamic fluid body interaction, coupling with other STAR-CCM plus models, so you can couple these SPH particles with another kind of Eulerian continua, do fluid structure interaction with the built-in finite element stress solver and conjugate heat transfer. Also, the current implementation is incompressible SPH. In future releases, they'll likely have a weakly compressible version of that, include non-Newtonian fluids, surface tension, and solid body contact. So a lot more coming, but the current implementation does have some exciting things about it, and I'll be giving a little demo of that right now. So I'll switch over to STAR here. Mark or Adam, can you tell me, can you confirm that you can see my STAR window?
Yes, I can see your STAR window.
All right, thanks so much. So right here I've got just a case kind of ready to go. So I'm showing here is just these two gears meshing here in this housing. And I'm just going to demonstrate real quickly how to set this simulation up and run it. And you'll see, how easy it is to put together one of these simulations. As it's, implemented in STAR, a lot of the operations are very similar to the ones that you're already used to when setting up a CFD simulation. So the first thing that I'm going to do is set up my continua. Just create a new physics continua. And as you'll see, it's very similar to other simulations. Then we just select SPH. I'm going to turn on this gravity and laminar, and we're good to go. Now, within the models, you might have noticed that a few things were automatically selected, one being adaptive time step provider. So this does not use a constant time step. You have to provide an adaptive time step provider. I'm going to use the convective CFL time step provider, and then another one which is based on the gravity and the acceleration of particles due to gravity. I am also going to just specify my phase. In this case, this is going to be oil, so I'm just going to modify H2O and throw in some more realistic material properties. See, this is much more viscous than water. And yeah, so that's it. Now, as I mentioned, a lot of this is very similar to setting up a just standard CFD simulation in STAR. One thing that is different is when we assign our geometry to regions. There's this new toggle here, which allows you to select between volume topology and surface topology. SPH doesn't, well, it requires you just to define the boundaries of the boundaries that the particles are going to be interacting with. And those boundaries don't even have to be watertight. So we're going to specify this as a surface topology because it doesn't need to know anything about volume. And now we've got our region set up. I'm going to rename that gearbox. And you may have noticed that I just created one boundary for all surfaces. That's because I'm going to specify any of the things that are particular to one part. I'm going to specify through the region using part subgroups. Just gonna whoops. We've got one subgroup now that contains all of the parts associated with this region. I'm going to create 3 subgroups. So now I can specify things within the region that are just particular to the gear or the pinion or the housing. So one other very necessary step is part orientation. So by default, when you create a geometry, the inward facing side of that surface is the outward facing side of that surface is the positive surface. And the SPH particles recognize a boundary by interacting with that positive surface. So we need to orient the housing to be so that the positive side is facing inward instead of outward. So that's set up. And then just one more step here. is specifying the rotation. So we want the gear and pinion to move. Should have named these. And I'm gonna say the gear is gonna move at negative 594 RPM with aligned with the y-axis. There we go. And the pinion to be consistent with that is going to rotate with positive 1,222 RPM. Okay, so now the motion is set up. The final step here is we need to define, where the particles lie initially. In this case, you do set up a volume part. I've created this oil initial condition, which is just it was an intersection between a block and the housing, and then I subtracted the part where it's interacting with the gear here.
Hey, Chris, this is Adam. Before you go on, there's an error in the bottom of your table down on the right.
I saw that. Yeah,
Can we ignore that?
Fixed that. Sorry. Yeah, I accidentally copied and pasted, but that's fixed.
Okay, good.
Yeah, this orange wasn't supposed to be there. Thank you. Yeah, so now we just want to specify the part that the particle generation is based off of. So I'm just going to select that oil IC, and I want to specify the particle size. So this is kind of what determines the discretization and the computational cost of your simulation. It also, determines the accuracy of your cost. Of course, if you make your particles smaller, it'll be more accurate, but more computationally expensive. For this demo, I'm going to choose 2 millimeter particle diameter. Then I will go ahead and I've set up a few scenes here ahead of time. I'm just going to go ahead and initialize this. And I'll just point to our geometry. See, there we go. So here's our particles in their initial condition at the bottom of the gearbox. And as I push go, the gears are going to start turning, and the particles are going to respond and start wetting the gears. As you can see, I've set the simulation to run for a half second here, and this is moving quite quickly. We're already a fifth of the way through. I also set up if I didn't forget a step here, I also set up a gear torque monitor so we can, I'm monitoring the amount of torque on that large gear. And as time progresses, it gets a little bit more fun. There's particles bouncing around the domain and between the gear and pinion. And there we go. I wasn't timing myself, but within a matter of minutes, we were able to set up this simulation, and it's almost run to completion, which is really spectacular. And I'll show you kind of some reasons why. So I ran this a few different times with different size particles and resolutions, I guess. And the one on the left, the very left, that was 2 millimeter particles. That's the one that I just showed you. It ran in a matter of seconds, and gave a torque that had kind of in the ballpark of what the one on the right produced, which took a number of hours. I should have mentioned this is just using 6 cores on my local machine here, but it took around 20 CPU hours to run that. But in any case, all of these are producing reasonable predictions in a very short amount of time. And to kind of demonstrate that, I wanted to see what my previous approach would have been if I didn't have SPH. I would have done this in using a volume of fluids model, and this makes things much more complicated. So shown here is the same exact problem, but I'm using volume of fluids. So I have to, one, represent the rotating gear and pinion on the background kind of housing domain using an overset mesh. So that's what's shown in the upper right there. I also am using adaptive mesh refinement to capture the free surface, and then also make sure that there's high quality interpolation at the overset interfaces. So we're pretty much remeshing every time step there. And anyway, I ran this for a few days on my local machine, and it really didn't progress as far as the others. And I estimated from that performance that this would take over 6,000 CPU hours to run with volume of fluids, whereas it took 20 CPU hours with the highest resolution SPH simulation that I did. So that really kind of drives the point home of where the value is with this approach. It's just very fast, and even though it ran quickly, it produced similar predictions on the gear torque to what I was getting from the volume of fluid simulation. So yeah, just to wrap things up, we've shown here that SPH, at least in powertrain simulations, can result in very large efficiencies. As more models get included in STAR-CCM Plus, you can apply SPH to a number of other problems as well. So that at the end, the implementation will have very comparable capabilities to SPH Flow, and you can use it for a lot of different things. Anyway, yeah, so SPH has been shown to be very efficient for predictions, including free surfaces, and I'd urge you all to take a look at it if those are the types of problems that you're solving, because it really saves a lot of time. Anyway, that's the end of the presentation here, and any one of us would be happy to take any questions.
Excellent, thank you, Chris. If anyone in the audience or the attendees have questions, please put them in the chat now. To preempt that, I have a couple for you, Chris. One is, I know it's brand new, but how familiar are we with the HPC scalability of this? If you can you put it on 1,000 cores and expect good speed up, or is it too new for us to know that yet?
I expect so. It's supposed to be very, very easily parallelized. I think Mark has more experience with that. So Mark, do you have anything to add or back me up?
Yeah, no, that's correct. SPH is extremely easy to parallelize and usually very fast when you scale it up. So yeah, I would expect to have maybe even better performance than mesh prefab methods or mesh-based methods when you start to parallelize.
Excellent. And then another question that I had, that in fact Manuel has asked as well. We've got a question on the chat, and he's asked 3 questions. One is how much is the cost? I'll get back to you on that, Manuel, about the cost of adding a SPH to a STAR license or the standalone. Really and it depends how you want to buy it in terms of cores and subscriptions and so forth. The regular conversation. The next question you had was, are you able to specify the contact angle in each surface? Chris or Mark, does that make sense to you in terms of what that means?
Yeah, I can answer that. So one of the models that will be, implemented in the future, so I'm basing these assumptions when I say this should be available in the future. It's based off of what is currently available in SPH Flow. And so one of those is surface tension, and once that becomes implemented, then the contact angle should become a parameter that you can set in STAR-CCM Plus when using the SPH model. Additionally, it currently isn't possible to couple this with the Eulerian flow field. Say if you had whatever, air and water interacting or something, it cannot yet do that. But in the future, you should be able to. Definitely.
It's interesting though that you can do that with DEM right now, and so obviously the techniques for coupling them is known to the development team from their DEM work. So I'm sure it's coming.
Right. Yeah, I don't think it's any technical shortcomings. It's really just it takes time and good organization to make sure everything is done correctly. So it's just on the roadmap.
Excellent. All right. Well, just a last call for any other questions. All right, there's no more in the chat, so we appreciate your time, everyone. Thank you for joining us this afternoon, and we will close the webinar. Thanks again.
Thank you.